This video is about working with formulas, and the formula that we'll use for our example is this formula that can be used to approximate the speed of a vehicle by looking at the tire skid marks. This formula says L equals V sub 0 squared over 30 FB. Here's what each of the variables stands for. L is the length of the skid mark measured in feet. V0 is the initial velocity, or the speed of the vehicle when it starts to brake. That's measured in miles per hour. The coefficient of friction and the braking efficiency are numbers between 0 and 100%. In the formula, we want them to be in decimal form, so they'll be numbers between 0 and 1. The coefficient of friction would be a high number if the tires grip the road very well. It would be a low number if the road conditions or tires make it very slippery. So a high coefficient of friction, like a 0.8 or a 0.9, would mean that the tires are gripping the road very well, and it's not very slippery. But a low coefficient of friction would mean that conditions are very slippery, that the tires are not gripping the road well. Braking efficiency is similar. It's another percent, but it's a percent based on how many of the tires are actually being used to brake. If all 4 tires are used to brake, the braking efficiency is 100%. If only the front 2 tires are being used to brake, efficiency is only at 60%. If only the back 2 tires are being used, the efficiency is 40%. So we've defined what each variable stands for. L is the length of the skid mark. It has to be measured in feet. V sub 0 is the initial velocity. Now this 0 is just a label. 0 to indicate that it's the original speed, original velocity. So the 0 won't have any impact when we do our calculating, but notice that the formula does have velocity squared, and we will need to use that exponent of 2. In the denominator, 30 times F times B, and F and B are both numbers between 0 and 1 to represent a percent. How much friction is there on the road to help a car stop, and how efficient is the braking of the car? How many tires are being used in the braking process? Now this formula is currently solved for L. We say that it's solved for L because the L is all alone on its side of the equation. So none of the other variables are solved for. The L is isolated, so we're solved for L. And when a formula is solved for a specific variable, it means the formula is set up well for us to evaluate all the other variables on the opposite side and calculate a value for L. So for an example, we could say, assume that the car was initially traveling at 30 miles per hour, and the coefficient of friction, will assume that it's a fairly good road, so we'll set the coefficient of friction at 0.85. No units on the coefficient of friction, it's just a percent. The same with braking efficiency. Let's assume that all 4 tires are being used, so we have an efficiency of 100%, but remember we need to use a decimal form, so we'll use 1 whole. Now we can evaluate this right side of the equation by substituting these values in place of the variables. I think it's a good habit when we're substituting numbers in place of variables that we do that inside parentheses to keep it clear what operations we need to do. In the formula, 30FB means 30 times F times B. So when I substitute those numbers in parentheses, it's still clear to me that we need to do multiplication in the denominator. And we have this exponent in the numerator. So taking care of the exponent in the numerator first, 900, and now we'll multiply the 3 factors in the denominator. 30 times 0.85 times 1 equals 25.5, and now we can divide. Numerator divided by denominator equals approximately 35.3 feet. We know it's feet because the formula was defined as using feet as the measurement of L. So we know feet are the units in our answer. So we've looked at an example where we picked values for each of the variable, plugged those values into the formula, and we were able to come up with a value for L. But we can do some other things with formulas without needing to know exactly the value of every variable. We can use this formula to explore the relationships between some of these variables. For example, maybe we want to see how different braking efficiencies will affect the length of the skid mark. So we're interested in comparing how does the length of the skid mark L compare to the braking efficiency B. That means that we'll need to fix the other two variables, original velocity and the coefficient of friction. Okay? So if we want to show the relationship between just two of the variables, we're going to pick values for the leftover variables in the formula. So we need to decide what should the original velocity be for this experiment. We could keep using the 30 miles per hour for the original speed, and let's choose a coefficient of friction. Why not stay at 0.85? Now this isn't like the last problem, where we're going to choose a value for braking efficiency and then evaluate this entire fraction. It's different because we want to be able to compare the braking efficiency to the length of the skid mark, so we need to leave both of those variables in the formula. What we can do is plug in the information that we do know and simplify this formula. We've substituted 30 in place of v0 for an initial velocity of 30 miles per hour, and 0.85 in place of f for the coefficient of friction. We can do the exponent in the numerator, and we can multiply these two numbers in the denominator just to clean this formula up a little bit. 900 over 25.5b. And now we can use this simplified formula to look at the relationship between braking efficiency and length of the skid mark. We'll choose a few different values for braking efficiency. We'll choose 0.6, 0.4, and for each one we'll evaluate and find the value of L. Our previous example for evaluating actually was the one where we had 1 in place of B, braking efficiency, and we got to that 35.3 feet. Well, let's just do that again to make sure that we're still on the right path. L equals 900 over 25.5 times B, we'll use 1, and it does equal approximately 35.3 feet. Let's set up a table to organize our results. So I set up a table where we have a column to list our value for B, and then a column to list the value for L, the length of the skid mark in feet. When B equals 1, we have a length of the skid mark, 35.3 feet. Now we'll go through and find values of L when B equals 0.6 and 0.4. We'll be going back to this formula for L, 900 over 25.5b, but we'll be changing the value of B. Next, let's use 0.6. Following order of operations, we'll multiply these two in the denominator and then divide 900 divided by the result. 25.5 times 0.6 equals 15.3, and now 900 divided by 15.3 is approximately 58.8 feet. Let's put that into our table. So our value for L has increased when the braking efficiency decreased. Remember, we were saying a braking efficiency of 60% was when only the front two tires were braking. So the skid mark is much longer. It takes the car longer to stop. Next, we'll use 0.4 for braking efficiency, and hopefully we'll see that our value for L has increased even more. That when the efficiency goes down, it takes longer for the car to stop, so we have a longer skid mark. So now into the formula in place of B, 0.4. We'll multiply 25.5 times 0.4. It equals 10.2, and then 900 divided by 10.2 is approximately 88.2 feet. So at the lowest efficiency, when only the two rear tires are braking, the tires will leave a skid mark that is 88.2 feet, approximately. Now the fact that the length of the skid mark increased as the braking efficiency decreased is something that we would expect. As fewer tires are actually braking, it's going to take longer for the car to screech to a halt. And we would guess the same thing about the coefficient of friction. As the coefficient of friction gets smaller, it means the road is more slippery, so again, we would see a longer skid mark. So some variables have what we call an inverse relationship. As one value increases, the result decreases, and vice versa. Here we see as B decreases as we look down this column, as the values of B decrease, the values of L increase. And the opposite is true. If we go up as the values for B increase, the values for L decrease. That's the inverse relationship. We can spot this from our formula also. The L by itself is acting like a numerator. Just like if we wanted to make it look like a fraction, we could make it L over 1 to clearly see it's in the numerator. But a number that's not part of a fraction, and it works for variable too, If it's not part of a fraction, it's working just like it's in the numerator. But seeing f and b in the denominator tells us that they have an inverse relationship with L. As f increases, L decreases. As f decreases, L increases. Same thing with b. b increases, we saw that as b increases, L decreases. So those two have the inverse relationship with L, and values that are in the numerator would have what we call a direct relationship. Direct relationship means that as one goes up, the result also goes up. And if it goes down, the result also goes down. And that's exactly what we would expect for this situation. If you increase your speed, you will have a longer tire mark. And if you decrease your speed, you would have a shorter tire mark. That's the direct relationship. As v gets larger, so does L. As v gets smaller, so does L. But the opposite, the inverse relationship, occurs with these variables that are in the denominator. So another thing we'd like to know about formulas is that we can often spot which variables have a direct relationship, that as one goes up, the result also goes up, and which ones have an inverse relationship, that as the values go down, the result goes up. Or if these values go up, the result goes down. And we saw that with a few calculations that we did here. Making b decrease to a smaller number led us with increased results values for L.